And this is lesson 9.1, the kinetic molecular theory and properties of gases. So just a little review, kinetic energy from physical science is the energy of movement. So we're going to talk about the movement of molecules and then the properties of gases. So the kinetic molecular theory states that gases are small solid particles, either atoms or molecules, with a large volume of space between them. And there's no attractive or repulsive forces between them. So here I have diagrammed a solid at the molecular level, a liquid, and a gas. You can see that there is a lot of space between the particles. And also, this gas particle is not attracted to this one, nor is it repelled by it. They are independent in their movements and their structure. The second part of the kinetic molecular theory states that gas particles are in constant random motion, so they are always moving. And there's no pattern to their motion. The collisions are perfectly elastic, meaning they're going to bounce, and the kinetic energy is transferred without loss, so there's no loss of the kinetic energy. And then temperature is a measure of an increase in kinetic energy. So as the temperature increases, the kinetic energy is also going to increase, which is going to make the particles move faster. Now, as the particles move faster and they speed up, there's going to be more collisions with the side of the container and with another molecule, and that is going to eventually increase the pressure. So let's take a look at the difference between solids, liquids, and gases as far as shape, volume, and compressibility are concerned. So solids are very rigid, so they're going to have a fixed shape. Solids are not going to change shape. The volume is also going to be fixed since the shape is fixed, and we cannot compress a solid. Liquids, however, have an indefinite shape. They are going to take the shape of the container. However, their volume is going to be fixed. I can have 5 milliliters of water in a test tube, and I can have that same 5 milliliters of water in an Erlenmeyer flask. The only thing that is changing is the shape. The volume is going to stay the same. And we cannot compress liquids. Gases, the shape is indefinite, and it is going to fill whatever container it's in. The volume is also indefinite because it depends on the container it's in, because it's going to fill that up. Compressibility, yes, you can compress gases. So because it's going to take the shape of the container, take the volume of the container, we can have the same amount of gas in a larger container as well as a smaller container. And that is shown here. Gases take the shape and volume of their containers so they can easily be compressed. We have 13 molecules of gas here. We have a larger container, and we can decrease the size of that container, still have 13 molecules, and they're both filling the container, but the size of the container is different, so the volume is different, as well as the shape. So we have some different variables that are used to describe gas. We have temperature, which we represent with a capital T. The unit for temperature is either going to be in Kelvin or Celsius. And degrees Celsius. There's no degree sign on Kelvin. Pressure, that variable is represented with a capital P. And there are 4 different units of pressure that we're going to discuss. kPa, which is a kilopascal. PSI, which is pounds per square inch. Which, if you have filled your tires up with air at the gas station, you're using an air compressor, so compressibility of gases, but you're typically looking at it in a PSI. ATM represents atmospheres. And then mmHg represents millimeters of mercury. Hg is the symbol for mercury. And then volume is represented with a capital V. The units for volume are either going to be a liter or a milliliter. And then amount is represented with a small n, and the units will either be in moles or in grams. You're typically going to have to convert it to moles, just like you had to for the molarity equation. Now note, changing any one of the variables will result in a simultaneous change in one or more of the other variables. So if you get an index card, take an index card. We did this in class. Put P on one end, the T in the center, and the V on the other. And you can use this to determine how the variables are going to change. So for instance, let's take a look here. Oops, sorry, this way. Here, volume and pressure. We're looking at volume and pressure. So temperature is constant. What's changing from this picture to this is that the size of the container is changing, so the volume. So put your finger over the temperature, because that is what you are holding constant. So here's your finger, put it over the temperature. The volume is decreasing, and so if you put your finger over the T and slide V down, that's going to cause your pressure to increase. Now, here in our next picture, so volume is decreasing, pressure is increasing. Here, our volume is constant, but the temperature is increasing. And so, again, back here, oops, I keep going the wrong way, I'm sorry. Here, So in this case, temperature is changing, volume is held constant. So you're going to put your finger over V, you're going to press T up because it is increasing, and that is also going to cause your P to go up, so P is also going to be increasing. And then in our next picture, you cannot use your PTV card for this because this is looking at amounts. But you're increasing the amount of particles of gas, and so that is going to increase the pressure. Right, what is atmospheric pressure? Atmospheric pressure is the pressure exerted by air molecules in the atmosphere, and this results from collisions of air molecules with objects. So the cat here says that atmospheric pressure seems rather high today. Its head's a little flattened out there. So converting units of pressure. A lot of times we're going to deal with atmospheres. So we are going to work on converting our different units of pressure to atmospheres. So we don't have to do anything to convert atmospheres to atmospheres, but millimeters of mercury, 1 atm equals 760 millimeters of mercury. Kilopascal, 1 atm equals 101.3 kilopascals. And then PSI, 1 atm equals 14.7 PSI. And then if you would just make another row on your chart down below, we need to talk about one other unit of pressure for your assignment today, and that is a torr. So the symbol is TORR. 1 atm equals 760 torr. Okay, so now that we know how to what the conversion factors are, then we can do some conversions. We're going to set these up just like you would converting from a mass to number of moles. So we want to know how many millimeters of mercury are equal to 1.15 atm. So we're going to start with 1.15 atm. And we know that 1 atm is equal to 760 millimeters of mercury. So atm is going to cancel. 1.15 times 760 is going to give us 874 millimeters of mercury. In this next problem, we're going to have more than one step. So we're given 94.6 kilopascals, and we want to know how many millimeters of mercury. So you're going to start with the number and unit that is given to you, the 94.6 kilopascals. So 1 atm equals 101.3 kilopascals. But we don't want atm, we want millimeters of mercury. So 1 atm, just like we used up here, is equal to 760 millimeters of mercury. atm cancels, so we need to take 94.6 times 760 and then divide by 101.3. which is going to be equal to 709.7 millimeters of mercury. And then in our last problem, why don't you go ahead and pause the video and try to do this one on your own. Welcome back. We have 97.8 kilopascals. We want to convert it to ATM. So 1 ATM equals 101.3 kilopascals. Kilopascals cancel. 97.8 divided by 101.3 is going to give us, I believe it's 0.965 ATM. My calculator is dead currently, so we're going to go with that. Converting units of temperature, the equation is the Kelvin is going to equal degrees Celsius plus 273, or we can rearrange this equation to get degrees Celsius equals Kelvin minus 273. Why don't you pause the video and go ahead and try these. So 17 degrees Celsius plus 273 is going to give you 290 Kelvin. And then 128 Kelvin minus 273 is going to give you negative 145 degrees Celsius. All right, what is STP? STP is standard temperature and pressure. Standard temperature is going to be 0 degrees Celsius or 273 Kelvin. Standard pressure is 1 ATM or 101.3 kilopascals. And I just checked that last conversion problem, and 0.965 ATM is correct. So that's it for the notes for this lesson. You have practice in your packet, letter B, kinetic molecular theory and properties of gases, to complete, as well as these problems were the additional assignment given in class. So you can pause the video, write these down on a separate piece of paper, and turn them in next class. Thanks for stopping by. Have a great day.